comparing, okay, so extra credit project. Oh, any questions on this? Okay, here's the extra credit project. And I suppose I could make it something like 3% of the grade.
Yeah.
And since this is extra credit, so is that too generous, 3% for extra credit?
I thought you said 10%.
No, 3%. 3%. Yeah, 10% would be too generous for extra credit. So 3%. 3% is, of course, quite substantial. And so, compare reliability and cost and other related factors for the storage devices for magnetic storage, Now I'm basically thinking about removable hard disk. So the problem is you want to save. Okay, I say I'm considering the problem that you have a bunch of stuff, maybe photographs, videos that you want to preserve, documents for a long time. And question is, if you have external hard drive, and you have flash memory, and let's see, what's the third option? In the cloud. And let's see, is there any other better option? Save it on DVD discs?
There are some new technologies that some of them are not really, like some of them just really implemented in a limited area, but
other. And now for it to be a satisfactory extra credit project, I'm looking for some good data. So there has to be some good data, some nice tables, at least a diagram, and some good analysis, and it should be up to date. So if I give this report to someone, then it should be something that they can use to base their decision on. And in the size, it should be about 2 pages of the IEEE conference format. That's the approximate size I'm looking for. So anyway, so I thought I'll, for those who may be interested in extra credit project. Oh, and this would be due, I have to figure out what the due date, but this would be due around the same time when the progress report for the main project is due. In other words, you cannot do that near the end, so you have to do it sometime around now. Now let us look at redundancy. Generalized reliability computation. Now in many cases, I think you can use this generalized idea, and basically in a system you have this, that you have a, now this would be applicable to, for example, when you have coding theory. So right now, most of the cases we had considered, they involve replication. You replicate the whole thing, make copies of the whole thing. But here we are considering possibility when you don't replicate the whole thing, but maybe add a few bits and things like that. This will work for replication also. So this is general. So here you have a block which is non-redundant. And to that we have some additional hardware which represents redundancy. And let's assume they are encountering the same process, whatever that is. And here we have a unit, let's call it B3, and it does detection and correction. So question is, what can you say about the reliability in this case? Now notice that in this case you have to have probably a different definition of reliability. And let us assume that reliability is defined as probability of correct output. Now this is similar to transaction reliability, right? So we are not talking about reliability from 0 to t or such thing, but if you apply an input, what is the probability that you are going to get a correct output? That is the question we are considering. Okay, so probability the correct output. Now there are two situations when the output would be correct. One situation is when everything is good. So probability when B1 is good and B2 is good and B3 is good. Plus. Of course, when everything is good, then it's working. Other possibility is that when B3 is good, now I'm abbreviating here a little bit, and for some failure mode here or here, there is some failure mode that can be corrected. So multiplied by I equal to 1 to n, and so these are, here we are referring to different failure mode I. Probability failure mode I, and it's multiplied here. Sorry, I have to kind of write it down here. Multiplied by probability that the failure mode I is correctable. Okay, what do you think about this? Do you agree? So the good states include when they are all good. And if you have a certain type of failure, probability that you have a certain type of failure multiplied by the probability that it can be corrected. And of course, this has to be good. If this is bad, then of course nothing works. And now we can, in short, represent that expression in this way. So the reliability of a system is equal to reliability of R1, R2, R3 plus R3 I equal to 1 to n. Probability that you have failure mode I, so I'm calling it P sub I. Okay, probability of failure mode I, I'm calling it P sub Fi, and probability that failure mode I is corrective. So it's the same thing as what I have here, except that I have a compact expression. Now, so let us assuming that R3 is 1. If you assume that reliability of this unit is perfect, then we can, and if a single failure mode dominates, then this we can write as probability of that failure mode and multiplied by probability that it can be corrected. Now let us apply it to memories with an error detection correction scheme. Now how many of you have heard about error detection correction scheme in memories? So that is something that is used in some memories. So most of the ordinary PCs don't have a correction thing built in. They just have a parity bit so they can do detection. But some high reliability systems, they can have a correction thing built in. So you will need to provide some extra bits, enough bits that are needed for correction. And then you need to have some hardware that will do the correction. And actually in the past, when they first came out with memory error correction units, things were not that good because they would build this unit using a number of small different components. But when they were able to put a lot of things on the same chip. So if you have a single chip, then things are much more reliable compared with when you have a number of different transistors or chips. So that made this scheme, error detection correction scheme, much more attractive. Now for quite a while, people who are working on manufacturing semiconductor memory, they were able to reduce the soft failure rate significantly. So with memories, you can have two types of failures. You can have a soft error, which is very common, that a bit gets flipped, but the hardware is still okay. And after a while, the error will go away, but the fault will go away, but the error may stay because it has already flipped a storage element. So you have to guard against that. So error correction can be quite effective for such temporary failures. If you have a permanent failure, then a particular memory bit is always wrong. Okay. So let's consider an example. A memory system now, I forgot to mention an important thing. In the last few years, like last 5-7 years, problem with soft errors have become more severe because the device dimensions have been decreasing. So they are now more susceptible to soft failure. So whenever there is a charged particle that hits a storage element, now the charged particles are everywhere. There's almost nothing you can do that will eliminate them. So they're a bigger problem probably in space where there are more charged particles, but even in normal atmosphere, you always have charged particles coming out of everything. So this piece of paper, so there's some charged particles coming out of here all the time. And the material that encapsulates the IC chip, that is releasing charged particles. So people have found that because of the smaller dimensions, it has again become a significant problem. But anyway, coming back to our analysis. So let's say memory system, we have a total of n bits per word. And let us assume that RB is reliability of a single I seem to have some mistake here. Reliability of a word. RB is reliability of a single bit. I think I have some error in my notes here.